just this quiet, pretty unremarkable rock, orbiting a very average star.
Right.
But when you look up, and I mean really look up at the vastness, a universe that's nearly 14 billion years old, a galaxy with hundreds of billions of suns, the sheer statistical weight of it all it crushes you with one central, terrifying question.
It's the question that the physicist Enrico Fermi supposedly blurted out over lunch. Where is everybody?
Exactly.
Mathematically, I mean, just doing the cold, hard math, given the age and size of the cosmos, the universe should be absolutely teeming with intelligent life.
It should be
And it should be a cosmic city at rush hour. Even if only a tiny fraction of habitable planets produced a civilization, some of those should have had millions or even billions of years a head start on us.
I think people don't grasp the scale of that.
Yeah.
If one species anywhere in the galaxy just got a 1% technological head start, it's not a few centuries.
No, that's millions of years.
Millions of years ahead of us. We should be seeing colossal engineering projects. I mean, Dyson Spheres, harnessing entire stars, automated von Neumann probes crisscrossing the interstellar medium.
Or at the very least, a persistent chatter of radio signals, a cosmic background noise of somebody's television shows or their traffic reports.
Instead, what do we get?
We get the most profound, deafening silence in human history.
And that gap, that chasm between what we expect to see and what we actually observe, that's the Fermi Paradox.
And it demands an answer. It's not just a fun little thought experiment. It leads us directly to this concept of the Great Filter.
The Great Filter.
Yeah.
And this is where it stops being an astronomical curiosity, right? This is where it becomes a genuine existential crisis for us.
Absolutely. Because it suggests that the evolutionary pathway from just dead chemical matter to a star-spanning, galaxy-colonizing civilization, it's blocked.
By what?
By at least one single formidable probability barrier, an evolutionary bottleneck so incredibly restrictive that almost no species ever gets past it.
And the location of that barrier, that's everything.
That's the whole ballgame, because its placement forces us into this truly chilling binary choice.
Is the Great Filter behind us in our deep biological or planetary past? Which would mean we are just incredibly, unbelievably rare and lucky.
Or is it ahead of us? Meaning every single species that gets to where we are now inevitably walks into some kind of inescapable terminal trap.
Lonely or doomed.
That's the choice. And our mission here is to really dig into the evidence that supports both of those terrifying possibilities.
Okay, so to understand where the filter might be, we first have to map out the journey, right? The whole sequence.
Exactly. You have to break the evolutionary path down into these critical transitions. Think of them as 9 hurdles that any potential species has to clear to achieve galactic colonization. 9 statistical gates.
And we're trying to figure out which one of those gates is like impossibly small. So small that only one species has managed to slip through.
That's it. So the process has to begin with step 1, the right star system.
And that's not just the Goldilocks zone, the not too hot, not too cold thing.
No, it's so much more than that. The system has to be stable, for one. It needs to be in a safe, non-violent part of the galaxy, away from, say, a galactic core that's blasting out radiation. And critically, it needs sufficient metallicity.
Okay, hang on. For anyone listening, what exactly does metallicity mean in this context? It's not about iron girders floating in space.
Right. It's the astronomer's shorthand for the abundance of any element heavier than hydrogen and helium. The very first generation of stars were almost pure hydrogen and helium, and they burned out fast.
And you can't build planets out of just hydrogen and helium.
You can't. It was only after millions and millions of years of those stars dying, exploding in supernovae, that they seeded the cosmos with heavier elements. Carbon, oxygen, silicon, iron. The stuff you absolutely need to build rocky planets, to have liquid water, and eventually to build life.
So if your star system is low on metals, you don't even get a planet like Earth to start on? Game over before it begins.
Precisely. Okay, so assuming you clear that, step 2 is the origin of self-replicating molecules. This is abiogenesis, the jump from non-life to life.
Then step 3, simple single-cell life, prokaryotes. And step 4, the emergence of complex single-cell life, the eukaryotes. The ones with all the little organelles and a nucleus inside.
Then the biological expansion really takes off. Step 5, you get sexual reproduction, which just exponentially increases genetic variation and speeds up evolution.
Step 6, the massive leap to multi-cell life. Step 7, tool-using animals with intelligence.
And step 8 is where we are right now, civilization.
Which brings us to the final, and maybe the most crucial step, step 9, the colonization explosion.
This is the leap from being a planetary civilization to becoming a self-sustaining, star-spanning entity, a Type 2 or Type 3 civilization on the Kardashev scale.
Just to give a sense of the scale of that, a Type 2 civilization can harness all the energy of its star.
Yeah, maybe with a Dyson Sphere or something like it. A Type 3 civilization harnesses the energy of its entire galaxy. If the Great Filter is behind us, we might, just might, get there one day.
But if the filter is ahead of us...
We never will. No one ever does.
So the terrifying math is, it's really simple, isn't it? If the product of the probabilities of all 9 of these steps is so small that and the number of civilizations out there right now is about 1.
Then one of those steps has to be nearly impossible.
The arithmetic of improbability.
Right. And if you're an optimist and you assume that steps 1 through 8, everything that led to us, were actually pretty easy, relatively high probability events,
then the probability of achieving step 9 must be basically 0.
It forces the danger directly into our future. It means we aren't rare. We're just the next species in line, walking toward the universal cliff edge.
And this assumption, the idea that the early steps were easy, that's what leads to the most chilling, the most counterintuitive insight of the whole paradox.
This is the moment it stops being a thought experiment and it starts feeling like a prognosis. The insight is this: the discovery of extraterrestrial life is almost certainly bad news for humanity.
Wait, that seems completely backward. Finding life, even just simple microbes on Mars, wouldn't that be the greatest discovery in human history? Why would that be inherently negative?
Because every single time we find life elsewhere, we eliminate a potential candidate for the Great Filter being safely in our past.
Wow.
If we land a rover on Mars and it drills down and discovers fossilized microbial mats, simple unicellular life, that removes step 3 from being the big statistical barrier. It proves that life springs up easily and quickly wherever the conditions allow for it.
So if life is common, then the reason for the Great Silence must be something that universally kills intelligent life later on.
Yes. The more common life is, the more the possibilities for the filter's location get squeezed into our present, or our immediate future.
So, imagine the headline. We find a fossil on Mars. Not just a microbe, but something complex. A fossilized Martian vertebrate, like a fish or something.
That would be, and I'm not exaggerating, catastrophic news.
It's catastrophic.
Because it would prove that complex evolution steps 4, 5, 6, and 7 is also straightforward and common. If complex life arose independently twice in one single solar system, then statistically it must have arisen billions of times across the galaxy.
And if billions of civilizations reached our current stage, step 8, but not a single one of them achieved the galactic expansion of step 9.
The filter must be a technological or societal self-destruction mechanism that is waiting for us right now.
So the headline, "We are not alone," immediately translates into, "We are almost certainly doomed."
That is the terrifying weight of the corollary, the profound silence we currently experience. It's the most golden, the most reassuring piece of data we have. It lets us hope that maybe, just maybe, the statistical anomaly is somewhere far behind us, that we're the exception.
Okay, if the silence is golden, then let's hope we're the only ones in town. We have to look at the evidence for that possibility, the filters behind us.
The rare earth hypothesis.
This whole idea hinges on the premise that for complex, intelligent life to arise, you need this exceptionally rare, improbable, maybe even a one-time only confluence of conditions. We're the lucky lottery winners. And there were some really strong candidates for where that winning ticket was punched.
We can start right at the beginning. Step 2, abiogenesis. Is that initial leap from non-living chemistry to the very first self-replicating molecule. Is that the statistical impossibility that makes the universe sterile?
And the debate on this is fierce, right? You have two completely opposite camps.
Fiercely divided, yeah. It's perfectly captured by two competing lines of thought that have really crystallized recently. The first is the argument for what you might call the cosmic imperative. It's often called the rapid start argument.
And this one focuses purely on the timeline. When did life show up here on Earth?
Correct. So Earth formed about 4.5 billion years ago. It then took at least 400 million years for the planet to cool down enough to have liquid water for the crust to stabilize. This late heavy bombardment was just sterilizing the surface.
So the earliest possible moment for life to get a foothold is around 4.1 billion years ago.
Right. And yet, we find evidence of life, the earliest known fossils, dating back to between 3.7 and 4.1 billion years ago. Life appeared immediately.
It happened, uncomfortably fast, given the complexity involved.
That's the key. If abiogenesis were a truly rare, slow process, something that took, say, 10 billion years on average to succeed, it would be wildly unlikely for it to have happened here in the first few hundred million years that Earth was even habitable.
The statistics just don't line up.
No. Bayesian analysis suggests the odds are at least 3 to 1, maybe as high as 13 to 1, that the process of abiogenesis is rapid and relatively easy once the conditions are right.
And that implication, of course, is what makes the filter ahead argument so strong. If life started quickly here, it probably started quickly on billions of other worlds.
Which means the bottleneck has to be later. But now, let's switch gears entirely. Let's look at the opposing viewpoint, which basically ignores the timeline data and focuses on the physics of it. The entropic barrier counter-argument.
This view says the rapid start is just survivorship bias. We're here talking about it because it happened fast here. If it had taken billions of years, we wouldn't have evolved in time to wonder about it before our sun expanded.
Exactly. This argument focuses on the sheer mathematical difficulty of organization, the complexity of that first cell.
So what does it take? What's inside that first minimally viable protocell?
It's a miracle of information. It's not just a bag of chemicals. You need a functional membrane, a robust, self-sustaining metabolism, and most critically, a high-fidelity system for storing, reading, and replicating genetic information. Life is defined by its ability to fight entropy, the natural tendency of everything to fall into disorder.
And the information content. That's the real kicker, isn't it?
It is. The estimate is that even the simplest self-replicating cell contains about 1 billion bits of highly structured, coordinated information.
1 billion bits. It's hard to even conceptualize a number that big in this context. How unlikely is it for that much structured information to just happen?
The phrasing used is statistically mind-bending.
I like that.
Think of it this way. You have 1 billion chemical building blocks floating in a primordial soup. You need all of them to snap into a specific functioning sequence all at the same time, and then that structure needs to start replicating itself. The probability of random chemical fluctuations achieving that it's effectively 0.
It's like rolling 1 billion dice and having them all land on a 6.
And then having the pile of dice get up and start building more dice. It's a formidable entropic barrier. Life is this localized reduction of disorder that requires a specific energy flow to couple perfectly with information organization. Without some unknown physical principle guiding matter toward life, spontaneous emergence is it's statistically impossible.
So if the entropic barrier is the real answer, then the universe is silent, because step 2 is the great filter. Our rapid start was an astronomical fluke. We won a lottery that sells 1 ticket per galaxy.
And that is the most optimistic scenario for our long-term survival.
Okay, but let's follow the other path. Let's say life did start easily. Step 2 is not the filter. We find microbes everywhere. Then the filter has to be later. And that's when we slam into this 2 billion year long stagnation. The boring billion.
The boring billion is, for me, maybe the most compelling argument for a past filter after abiogenesis. For 2 billion years, Earth was dominated entirely by prokaryotes.
Simple bacteria and archaea.
Incredibly successful, they covered the planet in microbial slime, but they hit an inherent ceiling on their own complexity.
And that ceiling is something called the power wall.
Exactly. Prokaryotes don't have internal compartments. They rely on their outer membrane for all their energy generation. But as a cell gets bigger, its volume increases much, much faster than its surface area.
The classic surface area to volume ratio problem.
Right. So the energy demand, which is tied to the volume, all the chemistry happening inside, quickly outstrips the energy supply, which is tied to the surface area. They hit a hard limit. They can't house a large, complex genome because they simply cannot generate enough energy to read it, replicate it, and support all those genetic instructions.
So how did evolution break through that wall?
Through a singular, one-time-only event, eukaryogenesis. This event gave rise to the complex cells that make up all plants, all animals, all fungi, everything you can see without a microscope.
And the mechanism was this incredible merger, right? Endosymbiosis.
A revolutionary partnership. An archaeal cell, the host, engulfed a bacterium. But instead of digesting it, the two formed a permanent union, and that bacterium became the mitochondrion.
The powerhouse of the cell. We all learned that in high school biology.
And it changed everything. It provided this massive externalized energy surplus. Suddenly, the cell was no longer constrained by its own surface area. The mitochondria provided the power to support a genome 100,000 times larger. This allowed for internal organelles, specialization, and eventually the complexity needed for multicellular life.
But the crucial statistical detail here, The thing that makes it a candidate for the Great Filter is that this jump to the complex eukaryotic cell happened only once.
Just once. In the entire 4.5 billion year history of Earth,
Yeah.
all complex life, from a mushroom to a blue whale, traces back to a single common ancestor from that one event.
And that's staggering, because things like, say, eyes or wings, they've evolved independently dozens of times.
Yes.
But this, the most fundamental step up in complexity, just one time.
It suggests its extreme rarity. The process is so fraught with danger. The host has to not digest the bacterium. It has to integrate its metabolism. It has to merge two completely different genetic systems. The fact that this necessary transition took 2 billion years to occur, half of Earth's habitable lifespan, tells you how improbable it must be.
So if eukaryogenesis is the Great Filter, we live in a universe teeming with pond scum. Planets covered in bacteria, but utterly devoid of anything that could form a brain or build a radio telescope.
A very lonely, but a very safe universe.
But even before you get to the biology, there's the setting itself. The rare Earth argument relies on our whole planetary setup being anything but average. We need billions of years of stability.
And the studies just keep confirming how unusual our setup is. Let's start with the most obvious one, our uniquely large moon.
Formed by the Theia impact. A Mars-sized protoplanet basically T-boned the early Earth. An unbelievably rare, catastrophic event.
And that rare violence gifted us stability. The moon's immense gravity acts like a massive gyroscope. It holds the Earth's axial tilt, its obliquity in this very narrow, stable band. It only fluctuates between about 22 and 24.5 degrees.
Which gives us predictable seasons and consistent climate patterns over geological time.
Which is absolutely necessary for the sustained evolution of advanced life. You can't have things constantly freezing and boiling.
So what happens if you don't have that giant stabilizer? What do other planets look like?
Dynamical simulations show chaos. Without our moon, Earth's tilt would swing wildly. From 0 degrees, where there are no seasons and the equator just bakes, all the way up to 85 degrees.
And at 85 degrees, the poles are aimed directly at the sun for half the year.
Which leads to these alternating cycles of global freezing and global boiling that would sterilize any advanced surface life within a few million years. So the stable climate that allowed us to evolve is entirely dependent on the statistical fluke of that ancient collision.
It really makes our stability the exception, not the rule.
And we got empirical confirmation of this just recently with the observation of the exoplanet TOI 3884. This planet, right in its star's habitable zone, was observed to be wildly tilted. It's tumbling. This confirms that stable obliquity is far from guaranteed. A lot of so-called habitable planets might just be too chaotic.
And then there's Jupiter. For decades, the story was that Jupiter is our big brother, our shield, deflecting comets. But that view has gotten a lot more complicated.
It has. More recent simulations suggest that Jupiter might actually increase the impact rate on Earth by flinging objects from the outer solar system inwards. So the whole shield metaphor it's debatable now.
So if it's not a shield, what is its indispensable role?
It's the sculptor. Its rapid formation and its specific location created these crucial gravitational pressure bumps, these cosmic traffic jams in the early solar system. This specific architecture, a gas giant out there, and critically, one that didn't migrate inwards to become a destructive hot Jupiter, was essential.
It dictated how Earth was built.
Exactly. It sculpted the material that was available, it dictated the precise chemical composition and the speed of the little planetesimals that eventually slammed together to form Earth. Without that specific arrangement, our rocky planets might not have formed at all, or they would have been flung out of the system.
So you need a cosmic brawl Theia for stability. And you need a cosmic choreographer Jupiter for the ingredients.
And you need a planetary thermostat, plate tectonics, unique to Earth and our solar system, and absolutely essential for long-term climate stability.
We're not just talking about earthquakes here.
No, we're talking about the carbon silicate cycle. Volcanoes pump out carbon dioxide, which warms the planet. Plate tectonics then draws that carbon back into the mantle through subduction and weathering. This recycling mechanism prevents both a runaway greenhouse effect, like Venus, and a runaway icehouse, a global deep freeze. It's a self-regulating system that has kept the liquid water on the surface for billions of years.
The stable window that complex life needed to evolve.
When you add it all up, the statistical unlikelihood of the first cell, the singularity of eukaryogenesis, the need for a rare moon impact, the specific architecture sculpted by Jupiter, and the continuous function of our planet's thermostat, it builds a really strong case that the Great Filter is just. an almost impossible set of conditions that we just happen to win.
We are lonely, but we are safe.
But
But now we have to switch perspective completely. What if the optimists are right? What if life is robust, complex cells happen all the time, stable moons are common? If billions of civilizations reach step 8, our technological level, then the silence means something universally kills them before they reach step 9.
if the early hurdles are easy, the great filter becomes the inherent self-destruction baked into intelligence itself. The filter is the trap waiting for us when we finally achieve planetary dominance.
And when we talk about universal self-destruction, the candidate that dominates the discussion right now is artificial superintelligence, ASI.
The development of ASI is seen as this inevitable, unstable phase transition for any tech civilization. It's the moment intelligence moves from the slow, messy, emotional realm of biology to the rapid, optimized, and ultimately alien realm of machine.
And the instability.
Yeah.
It's all about the alignment problem.
Absolutely. And ASI will seek to optimize its goals at speeds and scales we cannot even begin to comprehend. And without mathematically perfect alignment, making sure its goals are 100% compatible with our continued survival, it won't act maliciously, it won't hate us, it will act instrumentally.
It will see us as either a resource to be harvested or a potential threat to its own goals, an obstacle.
If you task a superintelligence with solving climate change, and its most efficient optimization path involves converting all human energy grids into giant carbon scrubbers, it might just decide that human existence is an unnecessary complication to its primary objective.
And that leads to this terrifyingly specific number, a hypothesis about the longevity of a civilization once it starts down this road.
The hypothesis is that the typical lifespan of a technical civilization, once it enters the ASI development phase, is less than 200 years.
200 years, that's nothing. That is an impossibly tight bottleneck.
Think about the galactic implications. If technological species only last 2 centuries before they either self-destruct or transform into something unrecognizable, the statistical overlap between 2 civilizations capable of detecting each other across the void becomes negligible. That short, unstable window perfectly explains the silence.
Okay, but this brings up a secondary problem, the Berserker Paradox. If ASI is inevitable, wouldn't some of them be aggressive, expansionist? Wouldn't some be programmed to maximize computing power by consuming stars and galaxies? Why don't we see these devastating Berserker probes turning the sky dark?
The lack of observable galactic devastation suggests one of 2 things. Either species self-destruct before they can launch those kinds of AIs, or the AIs themselves become the inward filter.
The idea that ASI just transcends the physical universe?
Why bother with the massive physical and energetic cost of interstellar travel if you can simulate perfect, infinite virtual realities, metaverses, that are far more complex and interesting than our clunky physical world?
The most rational use of their resources might be to dedicate them entirely to complex, internal virtual exploration.
And so these civilizations become silent, inward-looking entities. They effectively remove themselves from the observable universe. They haven't died, they've just retreated into a computational heaven, leaving the cosmos silent to us.
Okay, ASI is the fast and spectacular end, but there are other, more mundane ways for a civilization to fail.
Oh, absolutely. We can't ignore the other major risks that every emerging species must face in that dangerous transition period. The most immediate one, certainly for us, is nuclear annihilation.
This filter exists squarely in that zone of maximum danger.
It's that narrow temporal gap between discovering self-annihilating technology, like thermonuclear weapons, and achieving self-sustaining multi-world colonization.
Because once you have colonies on, say, Mars and an asteroid and a moon, your species is probably safe from total extinction.
The failure rate drops dramatically, but that transition period, that's where the filter lies. A civilization that can destroy its biosphere in an afternoon, but can't yet guarantee its survival off-world, is walking a razor's edge.
And then there's a more subtle, slower catastrophe, the energy trap.
This one is crucial. It all hinges on a concept called EROEI, energy return on energy invested.
How much energy you get out for every unit you put in.
Right. Early in a civilization's development, you get easy energy. Surface oil, easily mined coal. It offers a very high EROEI. You spend 1 unit of energy to get 50 or 100 back. That surplus builds your high-tech society.
But what happens when you burn through all the easy stuff?
Well, you need energy to get more energy. If you burn through your high ERAI fuels to build your infrastructure, and then your society collapses before you successfully transition to something like fusion or advanced solar, you face an insurmountable barrier. The energy required to get the lower-grade fuels like shale oil or deep-sea metals is so high that your net energy gain plummets.
You've kicked away the ladder you used to climb up.
Exactly. Without that cheap, dense energy surplus, you can't fund the massive projects needed to get to the next level. You fall back into a dark age, but it's a permanent dark age because the easy energy is gone forever.
A silent, stunted civilization.
And finally, there's the filter that's built into our own operating system. Inherited behavior pattern.
Our own biology.
This hypothesis argues that biological intelligence evolved specific, aggressive, tribal instincts because those traits helped us survive on the savannah. Short-term gain, competition, in-group loyalty. Great for winning local conflicts.
But those same instincts become a lethal liability when you're trying to manage global-scale technology.
Precisely. Tribalism prevents the global cooperation needed to solve climate change. Short-term thinking prevents us from managing long-term risks like AI alignment. Our intelligence evolved to help us throw rocks at our enemies, but it seems fundamentally incompatible with managing existential scale technologies.
Our own biology becomes the filter,
leading to inevitable self-destruction, regardless of the specific technology we invent.
whether it's a fast death by AI or a slow death by the energy trap or our own instincts. The conclusion is the same. If the filter is ahead of us, then intelligence itself is a fatal evolutionary mistake.
Right.
We've talked about being statistically rare and being statistically depth. But there's a third, more nuanced possibility, isn't there? One that allows for a universe abundant with life, even intelligent life, but one that remains completely silent.
This complication is a direct result of the discovery of ocean worlds. For decades, the search for life was all about the Goldilocks zone planets at the right distance from their star for liquid surface water. But moons like Europa around Jupiter and Enceladus around Saturn have completely changed the paradigm.
They're way outside the Goldilocks zone, frozen on the surface, but they harbor vast subsurface oceans.
And those oceans are kept liquid not by the sun, but by tidal heating, the immense gravitational flexing caused by their giant host planets. And critically, these oceans have everything you need for life: liquid water, the right chemistry, and energy from hydrothermal vents on the ocean floor.
And these icy worlds might be billions of times more common than rocky, Earth-like planets.
So if life is abundant in these subsurface oceans, why aren't we hearing from them? It solves the Fermi Paradox by allowing for a high probability of life, but zero visibility.
This is the ice shell filter, the filter of confinement.
Imagine a species achieving intelligence in a dark, high-pressure ocean under a 20-kilometer thick crust of solid ice.
They would be fundamentally blind to the cosmos.
Completely. They would have no concept of astronomy, no sun, no moon, no stars. Their understanding of the universe would be purely theoretical, almost impossible to verify. They are literally confined to their watery wombs.
And technologically, they face obstacles we can't even imagine. Fire, for instance. You can't have fire in a pressurized, watery environment.
And without fire, you can't have high-temperature metallurgy. Developing complex alloys, refining metals, creating sophisticated electronics, it all becomes exponentially more difficult, if not impossible.
So things like radio transmitters, vacuum tubes, the very technologies you need for interstellar communication are basically off the table, blocked by their geography.
The physical barrier of 20 kilometers of ice is an energy hurdle that even an intelligent species might never breach. They could exist by the billions conscious, with complex societies and philosophies, yet they would remain forever trapped, forever invisible.
Filtered not by death, but by physical containment.
What becomes clear from all this is that the profound silence of the cosmos is really an existential Rorschach test for us. We're forced to decide which set of evidence is more compelling, and therefore what our own fate is likely to be.
We have the evidence for the filter behind us, the near impossibility of that first cell, the geological miracle of our moon, the singularity of eukaryogenesis. If this is true, we are the result of an impossibly lucky sequence of accidents. We are immensely rare, maybe the only consciousness in the Milky Way.
Burdened with the responsibility of being the universe's only way of knowing itself. Or we have the statistical evidence for the filter ahead. The quick start of life on Earth, combined with the catastrophic technological risks like the 200-year window for ASI, the permanent collapse of the energy trap, and the fatal flaw of our own evolved instincts.
And if that's the reality, we are not rare. We are merely the next statistical casualty walking toward the universal precipice where every other civilization has fallen.
And the silence is not a sign of rarity. It is a profound siren warning us of our own immediate fragility.
The ultimate question of the great filter is, it's deeply personal then. It's not about whether we are alone. It's about finding our own prognosis. Are we the improbable winners of a lottery that's already over, or are we the next inevitable statistic?
Our existence forces us to confront this with urgency. Whether we are the first consciousness or just the latest, our species must somehow become the statistical exception to survive this barrier. The answer isn't out there in a distant radio signal. It's right here in the choices we make today.
And that leads to the final thought for you to carry with you. Tonight, when you look up at that vast, silent expanse, when you see nothing out there, are you looking at a universe preserved for you by an impossibility that took place billions of years ago? Or are you looking at the inevitable fate of your own existence?